What if the very fabric of time wasn't just a one-way street? What if you could step out of the present moment and walk freely into the past or future, witnessing historical events firsthand or glimpsing what lies ahead for humanity? It's an idea that has captivated storytellers, scientists, and dreamers for centuries, a concept that lives at the intersection of science fiction and cutting-edge physics. From H.G. Wells' iconic time machine to blockbuster films like Interstellar and Back to the Future, the allure of time travel speaks to something deep within us, a hunger to transcend our limits, to rewrite our mistakes, or simply to satisfy an insatiable curiosity about what was and what could be. But what if time travel isn't just the stuff of imagination? What if the laws of physics themselves hint that bending time might not be entirely impossible? For decades, brilliant minds have wrestled with this tantalizing possibility, exploring theories that stretch our understanding of reality itself. Some ideas emerge from the world of relativity and quantum mechanics, while others spring from more speculative yet mathematically sound corners of theoretical physics. Each theory offers a unique window into how time might be manipulated, whether through cosmic shortcuts, extreme gravitational fields, or mind-bending quantum phenomena. In this video, we're setting off on a journey through 30 of the most compelling theories that could explain time travel. We'll explore concepts ranging from wormholes and cosmic strings to closed time-like curves and quantum entanglement, diving into the science behind each idea while embracing the wonder and mystery that make this topic so endlessly fascinating. Whether you're a science enthusiast, a curious explorer, or someone who's always wondered if the future is already written, there's something here for you. So settle in, open your mind, and let's venture together into the realms of possibility where time itself may not be as fixed as it seems. Our journey begins not with a fantastical machine or a mysterious portal, but with a revolution in thought. In 1905, a young patent clerk named Albert Einstein published his theory of special relativity, and in doing so, he fundamentally changed our understanding of time itself. He proposed that time is not the universal, constant tick of a cosmic clock that Newton envisioned. Instead, time is relative. Its passage depends entirely on your state of motion. The faster you move through space, the slower you experience time. This incredible phenomenon is known as time dilation. To truly grasp this, let's explore the famous thought experiment known as the twin paradox. Imagine a pair of identical twins. One is an adventurous astronaut who boards a spacecraft capable of traveling at an astonishing 90% the speed of light. The other twin remains safely here on Earth. The astronaut embarks on a journey to a distant star and back. From the perspective of the Earth-bound twin, decades pass. They live their life, grow older, and see the world change. But for the astronaut twin moving at such an incredible velocity, time literally slows down aboard the ship. Their heartbeat, their thoughts, the aging of their cells, all of it unfolds at a measurably slower rate. When the traveling twin finally returns home, they step out of the spacecraft to find their sibling has aged decades, while they themselves have only aged a few years. One sibling is now significantly older than the other. This isn't science fiction. It's a direct prediction of Einstein's equations. We can visualize this by thinking of space-time as a flexible fabric. Objects with mass create dips and curves in this fabric, which we experience as gravity. But motion also interacts with this fabric. As an object approaches the speed of light, it's almost as if it's stretching the dimension of time, causing its personal experience of it to thin out and slow down. The most remarkable part of all this is that we account for time dilation every single day. The Global Positioning System, or GPS, that guides your car relies on a network of satellites orbiting Earth at high speeds. Because they are moving fast relative to us on the ground, their onboard clocks actually run slower due to special relativity. Furthermore, because they are farther from Earth's gravitational mass, their clocks run faster due to general relativity, which we'll discuss later. If engineers didn't constantly correct for these effects, the GPS signals would become inaccurate in a matter of minutes, and your navigation app would lead you astray by several miles. So, in a very real sense, time travel into the future is not just possible, it's a proven, operational fact of our universe. We are all time travelers moving into the future at the rate of 1 second per second. But special relativity shows us that by moving through space at high velocity, we can change that rate and take a shortcut into the future. But Einstein's revelation about the flexibility of time didn't stop with motion alone. A decade after his theory of special relativity, he unveiled an even more profound picture of the cosmos with his theory of general relativity. This framework proposed that gravity is not a mysterious force acting at a distance, as Newton described, but rather a consequence of the warping of spacetime itself by mass and energy. Imagine spacetime as a taut, flexible rubber sheet. Place a heavy bowling ball in the center, and it creates a deep indentation. Now, roll a marble near this curve. Its path will bend as it follows the contour created by the bowling ball. In this analogy, the bowling ball is a massive object like a star or a planet, and the marble is a beam of light or a smaller object being drawn in by the curvature, what we feel as gravity. This revolutionary idea completely reshaped our understanding of the universe, linking the force of gravity directly to the geometry of the cosmos. This warping of spacetime has a startling and direct consequence for time itself. General relativity predicts that gravity doesn't just bend the paths of objects and light, it also bends time. The stronger the gravitational field, the more time slows down. This is known as gravitational time dilation. Near an object of immense mass, like a planet or, more extremely, a black hole, the gravitational pull is so powerful that it significantly warps the fabric of time, causing clocks to tick much more slowly than they would in the emptiness of deep space. A perfect and popular illustration of this comes from the film Interstellar. The crew visits a planet named Miller's Planet, which orbits perilously close to the supermassive black hole Gargantua. The gravitational pull from Gargantua is so intense that for every single hour the crew spends on the planet's surface, 7 years pass for an observer back on Earth, or even for their colleague waiting aboard the ship in a higher orbit. This isn't just cinematic fiction, it's a dramatic but scientifically accurate portrayal of gravitational time dilation. The immense gravity of the black hole stretches time to an extreme degree, creating a heartbreaking scenario where a short expedition for one person translates into a lifetime of waiting for another. And just like with time dilation from velocity, this effect isn't merely theoretical. It is a measurable, everyday reality that we have to account for in our technology. Scientists have proven it using incredibly precise atomic clocks. In a famous experiment, one atomic clock was placed at rest on the ground, while another was flown on an airplane at high altitude. Because the clock on the airplane was farther from Earth's center of mass, it experienced slightly less gravity. When the two clocks were compared after the flight, the clock that had journeyed higher and experienced weaker gravity was ever so slightly ahead of its Earth-bound counterpart. Time had literally passed faster for it. This same principle is also crucially applied to the GPS satellites we mentioned earlier. While special relativity says their speed makes their clocks run slow, general relativity says their position high above Earth in a weaker gravitational field makes their clocks want to run fast. The net effect is that the gravitational influence actually wins out, and the satellite clocks run faster than those on the ground. Engineers must apply continuous corrections for both effects to ensure the system's stunning accuracy. So, every time you use your phone to navigate, you are personally benefiting from our understanding of Einstein's theories of time dilation. We are not just talking about abstract concepts confined to textbooks. We are discussing the verified, operational rules of our universe that allow for a very real form of time travel into the future, simply by moving through strong gravitational fields. While Einstein's theories show us how to journey into the future, they also hint at something even more astonishing, a potential path to the past. This brings us to one of the most iconic concepts in all of theoretical physics, the wormhole. First proposed by Albert Einstein and his colleague Nathan Rosen in 1935, these theoretical tunnels through spacetime are officially known as Einstein-Rosen bridges. Think of the universe not as a flat sheet, but as a vast, multi-dimensional apple. A worm is not limited to crawling along the curved surface. It can burrow a shortcut directly through the fruit's core, arriving at its destination in a fraction of the time. A wormhole proposes a similar cosmic shortcut, a tunnel that could connect two incredibly distant points in space, or perhaps even two entirely different moments in time. The mathematics of general relativity allows for such a structure. It would consist of two mouths, which are the entrances and exits connected by a throat. If you could enter one mouth, you would, in theory, emerge from the other almost instantaneously, even if those 2 points were separated by millions of light years. But here's where the plot thickens and the concept becomes truly mind-bending for time travel. According to the theory, if one mouth of the wormhole were moved at a significant fraction of the speed of light or placed in an intense gravitational field, time would pass at different rates for each end due to the effects of time dilation we just discussed. This would mean the two mouths are no longer just connected across space, but across time as well. Step into the mouth that has experienced less time, and you could exit from the other mouth into its own past. You wouldn't be traveling faster than light. You'd be taking a breathtaking shortcut through the very fabric of the cosmos. However, there is a monumental catch. The wormholes permitted by classical general relativity are notoriously unstable. The moment such a tunnel forms, it is predicted to collapse into a singularity faster than the speed of light, making it completely useless for any form of travel. Anything attempting to pass through would be instantly crushed. This is where physics ventures from the established into the highly speculative, yet mathematically fascinating realm of exotic matter. To prop a wormhole open and make it traversable, theorists propose that we would need a substance with a property that defies everyday experience, negative energy density, or what is sometimes called exotic matter. This isn't antimatter, which has positive energy and would still cause the wormhole to collapse. Exotic matter would possess a kind of negative or repulsive gravity, effectively pushing the walls of the wormhole's throat apart and preventing its instantaneous demise. While this sounds like pure fantasy, faint whispers of such phenomena exist even in established physics. The Casimir effect, a well-demonstrated quantum phenomenon, shows that two uncharged metal plates placed extremely close together in a vacuum can experience a faint attractive force because the quantum fluctuations between them have less energy than the fluctuations in the surrounding space. In a certain frame of reference, this can be interpreted as a region of negative energy density. While the amounts of negative energy generated are microscopic, it provides a tantalizing hint that the laws of physics might not entirely forbid the stuff you'd need to build a time machine. The challenge, of course, is finding or creating astronomical quantities of this exotic matter and then manipulating it to engineer a stable gateway through time. A challenge that remains, for now, firmly in the domain of theoretical exploration and our wildest dreams. Yet, even if we could somehow master exotic matter, the challenges of engineering a stable wormhole feel almost insurmountable. But what if the universe itself provided us with ready-made structures, cosmic artifacts so strange and powerful that they could twist time into a loop without any advanced technology? This brings us to another extraordinary proposal for a time machine, one that relies on cosmic strings. These are not the vibrating strings of string theory, but rather hypothetical, incredibly dense filaments thought to have formed in the earliest, most chaotic moments following the Big Bang. Imagine cracks or flaws frozen into the very fabric of space-time as the newborn universe expanded and cooled, like imperfections trapped in ice as it freezes. A cosmic string would be a flaw of unimaginable scale, potentially stretching across the entire universe. Despite being thinner than a proton, just a single inch of a cosmic string could contain more mass than Mount Everest. This incredible density means a cosmic string would warp the space-time around it with unbelievable intensity, creating a gravitational field so sharp it could literally bend light around it. It's this profound warping effect that opens the door to time travel. The immense mass of a cosmic string would curve space-time so severely that it could theoretically create what physicists call a closed time-like curve. In simple terms, this is a path through the universe that loops back on itself in time. If you were to follow such a path, you would eventually return to the exact same moment and location where you started, effectively traveling into your own past. It's a mind-bending concept where the future and the past connect, forming a loop without a beginning or an end. On its own, a single cosmic string might simply create a straight, incredibly deep trough in space-time. But the real potential for a time machine emerges when we consider not one, but two of these cosmic artifacts. Physicist J. Richard Gott proposed a brilliant and elegant model for how this could work. Imagine two incredibly long, straight, and parallel cosmic strings moving past each other at a velocity approaching the speed of light. Their immense gravitational fields would interact, twisting the space-time between them into an incredibly complex shape. Gott showed that if you were to fly a spacecraft in a precise figure-8 path around these two moving strings, you could effectively hitch a ride on this contorted region of space-time. Your journey would trace a path that is closed in both space and time. You would leave your starting point and after completing the loop, return to the exact same point in space but at a moment before you even left. You would have traveled into your own past, meeting your previous self. The beauty of this proposal is that it doesn't require any mysterious exotic matter or undiscovered physics. It relies purely on the established principles of general relativity and the hypothetical existence of these primordial strings. Of course, the obstacles are as enormous as the concept is fascinating. First, we have no confirmed observational evidence that cosmic strings actually exist. They remain a compelling prediction of certain cosmological models. Second, the engineering required to navigate such a path around objects moving at relativistic speeds is far beyond anything we can currently conceive. And finally, there are profound questions about the stability of such a system and whether quantum effects would prevent the formation of a closed time-like curve, protecting the timeline from paradoxes. Yet, the cosmic string time machine stands as a powerful testament to the creativity of theoretical physics, showing how the universe's own most extreme relics might hold the key to unlocking its greatest mystery. So if cosmic strings are elusive relics from the beginning of the universe, what if we wanted to build a time machine ourselves with our own hands? This ambitious thought experiment brings us to one of the most famous engineered time machines in theoretical physics, the Tipler cylinder. Proposed by physicist Frank Tipler in 1974, this concept pushes the mechanics of general relativity to their absolute limit. Imagine a cylinder of unimaginable density, perhaps constructed from the compressed remains of a neutron star. Now set this colossal object spinning, but we're not talking about a gentle rotation. The cylinder must whirl at a significant fraction of the speed of light, approaching velocities that defy all known engineering. According to Tipler's calculations, this incredible rotation would do something extraordinary to the fabric of spacetime itself. It wouldn't just spin on the spot, it would drag the very continuum around with it, like a gigantic spoon stirring a pot of honey. This phenomenon is known as frame dragging, a real effect predicted by general relativity that has been measured around our own rotating Earth, though on a vanishingly small scale. Around a Tipler cylinder, this frame dragging wouldn't be subtle. It would be so intense that it would twist the paths of objects and light into closed loops. If you were to pilot a spacecraft on a precise spiral course around this rapidly spinning cylinder, you could follow a path that curves not just through space but through time as well. Your trajectory would become a closed time-like curve, bringing you back to a point in your own past. You wouldn't be moving faster than light. You'd simply be navigating a course that has been twisted into a circle by the sheer rotational force of this cosmic object. It's a concept that feels both mechanical and magical, a time machine built not with flashing lights and levers, but with pure mass and motion. However, the practical hurdles shift this idea from the immensely difficult to the virtually impossible. The first and most obvious challenge is the cylinder itself. Tipler's equations show that for this effect to work and create a stable closed time-like curve, the cylinder must be infinitely long. Obviously, constructing an object of infinite length is a rather significant engineering problem. Even if we could somehow overcome that, the material requirements are staggering. The cylinder would need to be made of an ultra-dense material, something with the density of a neutron star, where a single teaspoonful would weigh billions of tons. We have no known method for creating or manipulating matter in such a state, let enough of it to forge an object of any length, much less an infinite one. While the Tipler cylinder remains a fascinating and important thought experiment that shows how the laws of physics might permit time travel under specific, extreme conditions, it also serves as a stark reminder of the chasm that often exists between mathematical possibility and physical practicality. It is a blueprint for a time machine that the universe's own rulebook might allow, but that its available materials and our current understanding of engineering simply cannot fulfill. But perhaps the most promising, and certainly the most terrifying, potential gateway through time already exists naturally in our universe, forged by the deaths of massive stars. We've all heard the warnings about black holes, that their gravity is so intense that not even light can escape, making them the ultimate cosmic dead ends. Yet, according to Einstein's equations, not all black holes are created equal. While the static Schwarzschild black hole is indeed a one-way ticket to oblivion, a rotating black hole, known as a Kerr black hole after physicist Roy Kerr, who discovered the solution in 1963, presents a far more complex and intriguing possibility. Its unique geometry doesn't just offer a point of no return, it might offer a passageway. The key difference is spin. A Kerr black hole isn't just a massive object sitting in space, it's a colossal vortex spinning at a significant fraction of the speed of light. This rotation fundamentally changes its structure. Instead of a simple spherical event horizon, the boundary beyond which escape is impossible, a Kerr black hole has a much more complex anatomy. First, there's the ergosphere, an egg-shaped region of distorted spacetime that surrounds the event horizon. Within this zone, the black hole's rotation is so powerful that it literally drags the fabric of spacetime around with it, a phenomenon known as frame dragging. Nothing here can remain stationary. Everything is forced to move in the direction of the spin, caught in a current of twisting spacetime. This isn't just a theory. We've measured this subtle effect around our own rotating Earth. But around a Kerr black hole, it would be an irresistible cosmic maelstrom. This incredible motion warps the black hole's interior as well. At the very center, instead of a point-like singularity of infinite density that would crush any matter into nothingness, the rotation flattens this ultra-dense core into a ring. This is the ring singularity, a donut-shaped loop of unimaginably dense material. And according to the mathematics, this ring doesn't represent an end but a potential doorway. The equations suggest that an object could, in theory, pass through the ring without being annihilated, emerging not into a crushing oblivion, but into a completely different region of space-time, perhaps another universe or even a different time in our own. It becomes a kind of natural wormhole, a built-in cosmic shortcut. However, embarking on such a journey would be the most perilous voyage imaginable. The regions inside a Kerr black hole, just outside the ring singularity, are predicted to be chaotic and violently unstable. You would likely be bombarded by incredibly intense radiation and subjected to tidal forces that could stretch and compress your ship and you like spaghetti. Furthermore, the stability of this entire structure is a subject of intense debate among physicists. Many theorize that the moment anything tried to pass through the ring, the interaction would cause the entire gateway to collapse, sealing the passage or worse. So, while the Kerr solution to Einstein's field equations mathematically allows for a traversable path, the physical realities of surviving the trip through the inner chaos of a rotating black hole remain a monumental and likely insurmountable challenge. It presents a tantalizing paradox, a natural time machine potentially built into the cosmos, but one that seems fiercely guarded by forces that would destroy any traveler daring enough to attempt the passage. Moving from the violent chaos of a black hole's interior to a more controlled, albeit still theoretical, form of travel, we arrive at a concept that feels like it was pulled straight from the most optimistic visions of science fiction, the Alcubierre warp drive. First proposed by Mexican physicist Miguel Alcubierre in 1994, this idea offers a breathtakingly elegant solution to one of physics' greatest commandments, that nothing can travel faster than light. Alcubierre's brilliant insight was that while nothing can move through space faster than light, there is no law against space itself moving faster than light. His concept doesn't break the rules of relativity, it cleverly bends them to create a cosmic loophole. Imagine a surfer catching a wave. The surfer themselves isn't paddling at an impossible speed. Instead, they're carried along by the motion of the water itself. The Alcubierre drive works on a similar principle, but the wave is a bubble of spacetime. Here's how it would function. A spacecraft would be nestled inside a region of flat, normal spacetime. Directly in front of the ship, the drive would cause the fabric of spacetime to contract, pulling the destination closer. Simultaneously, directly behind the ship, spacetime would be made to expand dramatically, pushing the point of origin farther away. The ship inside this warp bubble wouldn't be moving at all relative to the space immediately around it. It would be, in a sense, standing still. Instead, the bubble itself would be surfing this wave of distorted spacetime, carrying the ship along at velocities that could far exceed the speed of light. Since the ship isn't accelerating locally, the crew would experience no g-forces and, incredibly, no time dilation from high-speed travel. They could cross galactic distances in the blink of an eye without feeling a thing. This is where the connection to time travel becomes astonishingly clear. According to the principles of general relativity, if you can travel faster than light, you can also travel back in time. This isn't just a vague notion, it's embedded in the mathematics of space-time. An object moving on a superluminal path from the perspective of some observers could arrive at a destination before it even departed. Inside an Alcubierre bubble, you wouldn't just be crossing space at an incredible rate. You'd be carving a path through the four-dimensional continuum of space-time that could loop back on itself. By carefully manipulating your trajectory and the properties of your warp bubble, you could, in theory, set a course not just for a distant star, but for a specific date in history. You could return to Earth to find you've arrived a week, a year, or even a century before you originally left. The elegance of the concept, however, is matched by its immense practical challenges. The first and most daunting is the energy requirement. Alcubierre's original calculations suggested that creating such a warp bubble would require an amount of negative energy, that same exotic matter we discussed with wormholes, equivalent to converting the entire mass of Jupiter into pure energy. Later refinements to the math have brought that number down significantly, with some estimates suggesting the mass energy of something like the planet Mars might suffice, while other models propose configurations that could reduce the need to just hundreds of kilograms. But even the most optimistic scenarios still call for energies and materials far beyond our current grasp. We are talking about manipulating the fundamental fabric of the universe on a scale that is almost godlike. This leads directly to the second and perhaps greater obstacle, the exotic matter itself. We don't know how to create or contain the vast quantities of this material with negative energy density that would be required to stabilize the warp bubble and maintain its structure. While quantum mechanics hints that such energy states might be possible on a microscopic scale, scaling that up to power an interstellar starship is a challenge of an entirely different magnitude. Furthermore, there are serious questions about what would happen at the boundaries of the warp bubble. Some theories suggest that any particles collected along the leading edge of the bubble would be released in an incredibly energetic burst upon arrival, potentially vaporizing your destination planet in a cataclysmic explosion. Other analyses propose that the interior of the bubble would be causally disconnected from the outside universe, meaning you wouldn't be able to start or stop the drive. You'd simply be launched on a predetermined path with no way to control it. Despite these formidable hurdles, the Alcubierre warp drive remains one of the most compelling and actively researched ideas in advanced propulsion theory, a testament to our enduring desire to not only explore the stars but to master time itself. Now, as we shift our gaze from the cosmic scale of warp drives and black holes to the subatomic realm, we encounter a theory that turns the very concept of time travel on its head. This idea suggests that to journey through time, you might not need a machine at all. You might simply need to make a choice. This is the domain of quantum mechanics and the mind-bending many worlds interpretation. Unlike the theories rooted in general relativity, which bend space-time itself, this approach offers a solution to time travel's greatest logical hurdle, the paradox. What if you could never truly change your own past because every possible version of history already exists? To understand this, we first need to step into the bizarre and counterintuitive world of quantum mechanics. At the subatomic level, particles don't behave like tiny billiard balls. They exist in a blur of probability. An electron isn't definitively in one place around an atom's nucleus. It has a probability cloud, a set of odds for where it might be found when we look. Before it is observed, according to the classic Copenhagen interpretation, it exists in a superposition, a ghostly state of being in all possible positions at once. It's only the act of measurement that forces it to choose a single, definite state, collapsing the wave function of possibilities into one concrete reality. This always left a thorny question: what exactly constitutes a measurement, and what happens to all those other possibilities that were just as real a moment before? In 1957, physicist Hugh Everett Roman III proposed a radical and elegant answer: nothing is lost. Every single quantum possibility is realized. Every time a quantum event has more than one possible outcome, the entire universe splits, branching off into a nearly identical copy where each alternative happens. This is the many worlds interpretation. It suggests that our reality is constantly fracturing into a vast, ever-growing tree of parallel universes, a multiverse of unimaginable scope where every conceivable event plays out in some branch of existence. In one universe, you decided to have toast for breakfast. In another, nearly identical branch, you chose cereal. In one world, a cosmic ray missed a key molecule in your ancestors' DNA. In another, it hit and you were never born. This isn't just about human choices, but about every single indeterminate quantum event that occurs everywhere in the cosmos, every moment. The implications for time travel are profound and paradox-free. Imagine you built a device that could send you back to the year 1920. You arrive with the noble intention of stopping a great historical tragedy. In a single timeline model, your actions would create a paradox. If you succeed, you might erase the very reason you traveled back in the first place. But under the many worlds interpretation, the moment you arrive in the past and interact with it, you are no longer in your original history. Your very presence is a new quantum event causing the timeline to branch. You might succeed in your mission spectacularly, but you wouldn't be rewriting your own past. Instead, you'd have created a new, separate branch of reality where that tragedy never occurred. Your original timeline, with all its history and the version of you that left on this journey, remains completely untouched and unchanged. You could never return to it because your actions have anchored you to this new, divergent world line. This framework turns time travel from an act of editing into an act of exploration. You're not a historian changing a book, you're a reader jumping to a different volume in an infinite library, each telling a slightly different version of the same core story. You could even meet yourself, but it would be a version from a different branch, not your own past. This elegantly sidesteps the infamous grandfather paradox entirely. If you traveled back and accidentally or otherwise prevented your grandfather from meeting your grandmother, you would simply be creating a new universe where you are never born. The you that performed the act came from a universe where it did happen, and that timeline remains perfectly intact, its history secure. Of course, this theory raises its own profound and almost existential questions. If every possibility is realized in some branch, then there are worlds where you are a billionaire, worlds where you never existed, and worlds where dinosaurs evolved sentience and built civilizations. The sheer scale is humbling. Furthermore, the mechanism for how a time traveler would select or jump to a specific branch is completely unknown. It's a feature of the interpretation, not a described technology. There's also the unsettling thought that from a universal perspective, every decision you've ever made has a version of you that made the opposite choice, living a completely different life in a reality forever separate from your own. The many worlds interpretation doesn't so much solve the engineering problem of time travel as it dissolves the logical problems associated with it, offering a vision of reality so expansive and complex that the past isn't a single point to be changed, but an infinite tapestry of moments, each existing in its own right, waiting to be visited. While the idea of parallel universes offers one elegant escape from the paradoxes of time travel, another concept rooted directly in Einstein's equations presents the paradox in its purest form. This brings us to the deeply fascinating and philosophically challenging idea of closed time-like curves, or CTCs. To grasp this, we need to revisit our mental model of spacetime. We often think of a person's life as a line stretching from birth to death, with each event a point along that line. This is called a world line. Normally, this line only moves forward through time. It's an open curve. A closed time-like curve is exactly what it sounds like, a path through the universe that, if you were to follow it, would bring you back to the very same event in spacetime where you started. Your world line would form a loop circling back to meet itself. You would leave on a journey and return to the exact same moment and location from which you departed, having become your own past. These aren't just science fiction, they are rigorous mathematical solutions to Einstein's field equations of general relativity. They appear in the geometry around certain extreme massive objects, like the region inside a rotating Kerr black hole, or around the theoretical structures we've discussed, such as infinite Tipler cylinders or moving cosmic strings. The common thread in all these scenarios is an intense and specific warping of spacetime, often involving enormous mass and rapid rotation, that twists the fabric of the continuum so severely that the future direction literally bends around and connects to the past. Following such a curve wouldn't require exceeding the speed of light. You'd simply be moving along a path where the arrow of time itself has been coiled into a circle by the gravity of the object you're orbiting. This is where we encounter the most famous logical problem of time travel, the grandfather paradox. Imagine you have access to a closed time-like curve. You travel back in time to a point before your grandfather had children, and for whatever reason you prevent him from meeting your grandmother. This action would seem to create an impossible contradiction. If your grandfather never has children, then your parent is never born, and consequently, you are never born. But if you were never born, you could never have traveled back in time to interfere with your grandparents' meeting in the first place. So the event both must have happened and cannot have happened, a logical inconsistency that seems to violate the fundamental laws of cause and effect. So how does physics deal with this? One compelling proposal is the principle of self-consistency, most famously championed by physicist Igor Novikov. Novikov's conjecture essentially states that if closed time-like curves do exist, then the laws of physics must conspire to make them consistent. Any actions you take while in the past must end up being part of history all along. You could not change the past because you already did what you did. In the grandfather paradox scenario, this means it would be physically impossible for you to successfully interfere with your grandparents' meeting. Something would always stop you. Your gun would jam, you would slip on a banana peel at the critical moment, or you would have a sudden change of heart. Your free will to alter events would be constrained by the simple, ironclad fact that you exist in the future, so your actions in the past cannot be ones that prevent that existence. You are always part of the timeline, and your journey back is just an event that unfolded in a loop. This view treats the entire timeline as a fixed, immutable story where every event is locked in place, and time travel is merely a mechanism for participating in a predetermined past. Another, perhaps even more fascinating, resolution comes from the quantum world. At the quantum scale, particles are governed by probability. The grandfather paradox from a quantum perspective might be resolved through the sheer statistics of possibility. Imagine a particle traveling on a closed time-like curve. It goes back in time with the potential to interact with its younger self in a way that could prevent its own existence. Quantum mechanics suggests that when the particle arrives in the past, its interaction wouldn't create a single, definite outcome. Instead, it would enter a superposition of states, a probability cloud of all possible interactions. The mathematics shows that the only outcomes that remain stable and don't lead to paradoxical probabilities are the self-consistent ones. The wave function of possibilities for that particle would effectively collapse onto the one history where it did not create a contradiction. The paradoxical outcomes cancel themselves out through destructive interference, leaving only the consistent timeline as a real physical possibility. In this way, quantum mechanics might act as a cosmic editor, deleting any paradoxical timelines from the realm of what is possible, and ensuring that if closed time-like curves are real, they can only operate in ways that are logically coherent, preserving the fragile chain of cause and effect that defines our reality. But if warping space-time or finding cosmic strings feels like a grandiose endeavor, what about a far more subtle and fundamental approach to time travel, one that relies on a single hypothetical particle? This brings us to the enigmatic concept of tachyons. The name comes from the Greek word tachys, meaning swift, and these particles are theorized to have one defining, incredible property. They would always travel faster than the speed of light. In our normal world, massive objects like you, me, or a rocket ship can only approach the speed of light, requiring infinite energy to ever reach it. Tachyons, however, are theorized to live on the other side of that light-speed barrier. According to the equations, they would only be able to exist at faster than light velocities, and it would require infinite energy for them to slow down to the speed of light. This bizarre characteristic leads to an even more astonishing consequence for their relationship with time. One of the core tenets of Einstein's special relativity is that as an object's velocity increases, its rate of time flow decreases. We see this with time dilation, where a fast-moving astronaut ages slower. If we mathematically extend this principle to velocities beyond the speed of light, the equations suggest that for a tachyon, time would effectively run backwards. From our perspective, a tachyon's journey would be a trip into the past. Imagine one of these particles being emitted from a distant star and arriving at a detector on Earth. According to the math, the detection event on Earth could actually be the cause of the emission from the star, reversing the normal flow of cause and effect. This bizarre time reversal property immediately suggests a potential application: tachyon telegraphs. If we could create, detect, and control these particles, we might be able to encode a message onto one. A tachyon beam sent from a station today could, in theory, be intercepted by a receiver yesterday, allowing for communication with the past. The idea is scientifically intriguing because it emerges directly from the mathematics of relativity, not from science fiction. However, the vast majority of physicists remain deeply skeptical about the existence of tachyons, and for a very compelling reason. They threaten to shatter the foundational principle of causality. Causality is the simple, intuitive law that the cause must always come before the effect. You throw a ball cause, and then it breaks a window effect. A tachyon could turn this fundamental logic upside down. The most famous illustration of this problem is the tachyon antitelephone thought experiment. Imagine you have a device that can send and receive tachyon signals. You receive a message from your future self that says, "Do not, under any circumstances, use the tachyon machine today." Upon reading this warning, you decide to heed the advice and never send the message. But if you never send the message, then your future self could never have received it to send the warning back. You are stuck in a logical loop where the message both must exist and cannot exist, a paradox that makes the very concept of a stable reality seem impossible. This violation of causality is the primary reason tachyons have never been observed and are generally considered a mathematical curiosity rather than a serious physical reality. Searches for them have been conducted, often by looking for unique energy signatures that would be left behind if a faster-than-light particle interacted with normal matter, but all such searches have come up empty. The equations allow for them, but the universe seems to forbid them to protect the very order of cause and effect that makes existence coherent. Some theorists have proposed mechanisms to avoid these paradoxes, such as the idea that tachyon interactions would be so statistically weak or self-canceling that they could never be used to create a coherent, paradox-inducing signal. Yet, without any experimental evidence and with the heavy weight of causal paradox working against them, tachyons remain one of the most fascinating what-if scenarios in physics, a ghost in the machine of relativity that shows us just how deeply intertwined motion, time, and the unbreakable sequence of cause and effect truly are. Now, let's journey from the cosmic scale of closed time-like curves and hypothetical particles down to the subatomic realm, where the rules of reality become even more strange and counterintuitive. Here, we encounter a phenomenon so bizarre that it baffled even Einstein, who famously called it spooky action at a distance. This is the world of quantum entanglement, a concept that doesn't just challenge our understanding of space, but might also hold profound and unexpected implications for the nature of time itself, potentially offering a form of time-symmetric communication. At its heart, quantum entanglement is a connection between two or more particles that becomes so intimate that their fates are inextricably linked, regardless of the distance separating them. Imagine you create a pair of entangled electrons. Their properties, like their spin, are undetermined, existing in a fuzzy superposition of possibilities. But the quantum state that describes them is a single, unified entity. Now you physically separate these two electrons, placing one in a lab on Earth and the other on a spaceship headed for Mars. The incredible part is this: the moment you measure the spin of the electron on Earth and find it spinning, say, up, its entangled partner on Mars will instantaneously be found to be spinning down. This connection seems to happen faster than the speed of light, a notion that appears to violate the cosmic speed limit set by relativity. Einstein was deeply troubled by this, as it suggested information could be transmitted instantly, but decades of meticulous experiments have confirmed that entanglement is an undeniable feature of our universe. This is where the concept of quantum teleportation comes into play, and it's not the Star Trek style of teleportation you might imagine. Researchers aren't beaming people from one place to another, they're teleporting the quantum state of a particle. The process relies heavily on entanglement. You can use a pair of entangled particles as a resource to transfer the exact quantum information of a third particle to a distant location, effectively recreating its unique state elsewhere. The original particle state is destroyed in the process, adhering to the no-cloning theorem of quantum mechanics, but its perfect replica appears at the destination. While this doesn't involve moving matter through time, the mechanism relies on that same instantaneous, spooky link, forcing physicists to ask deeper questions about how information and influence are propagating. This leads us to one of the most radical interpretations of these phenomena, the idea of retrocausality. The standard view of physics is that causes always precede their effects. But what if, at the quantum level, that arrow of time is more flexible? Retrocausality is the proposition that a measurement made in the present could theoretically influence the state of a particle in the past. It suggests the future can reach back and affect the past. In the context of our entangled particles, one way to interpret the instantaneous correlation is not that information is traveling faster than light across space, but that the act of measurement in the present is defining what the state of the particle was at the moment of entanglement in the past. The effect, the measurement outcome, is determining the cause, the initial setup. This isn't just philosophical speculation. It's a framework some physicists are seriously exploring to resolve the paradoxes of quantum mechanics. The delayed choice experiments pioneered by physicist John Wheeler provide a compelling thought experiment that hints at this. Imagine a photon traveling through space from a distant quasar billions of years ago. It approaches a gravitational lens, a massive galaxy that bends space-time, which can force the photon to take one of two paths around it. Here on Earth, we can set up an apparatus to measure which path the photon took, confirming it behaved like a particle. Or we can set up a different interferometer apparatus that forces the photon to reveal wave-like behavior, showing that it somehow took both paths. The mind-bending conclusion is that our choice of measurement today seems to determine how that photon behaved billions of years in the past. The future observation is retroactively defining the past history of the particle. While this doesn't allow for sending a deliberate message to the past, the outcomes are still probabilistic and don't carry classical information. It profoundly challenges our classical, one-way view of time. It paints a picture of a universe where the present and the past are in a constant, subtle dialogue, with the future perhaps playing a more active role in shaping reality than we ever imagined. The quantum realm suggests that time might not be a flowing river but a vast, interconnected ocean where ripples can move in all directions, and entanglement could be the subtle current that connects moments across the depths of time itself. Yet for all its elegant resolution of paradoxes, the Novikov self-consistency principle presents a universe that can feel deeply unsettling. It proposes a reality that is fundamentally deterministic, a single, unchangeable timeline where every event is locked into place. Your journey back in time wasn't an alteration of history, it was always a part of it. The universe, in this view, operates like a perfectly crafted piece of music. You might think you're improvising a new melody, but every note you play was already written into the score. Your sense of free will, the feeling that you could have chosen to do otherwise, becomes an illusion. The principle suggests that the laws of physics would subtly guide your actions, not through some conscious force, but through an infinite web of cause and effect that ensures only consistent outcomes are possible. This doesn't mean your journey would be pointless. You could still go back and witness historic events, or even fulfill a role you didn't know you played. Perhaps the mysterious stranger who saved your grandfather from a falling beam was always you, fulfilling a predestined loop that ensures your own birth. Your actions would have consequences, but they would be the same consequences that always happened, reinforcing the timeline rather than rewriting it. This creates a fascinating and rigidly coherent universe, but one that leaves no room for true change or alternate possibilities. framing our lives as participants in a story whose ending was written into the fabric of space-time at the very beginning. But what if the universe itself has a built-in security system, a set of physical laws specifically designed to prevent paradoxes and protect the integrity of causality? This is the fascinating and somewhat sobering idea proposed by the legendary physicist Stephen Hawking, known as the chronology protection conjecture. After examining all the theoretical pathways to the past we've explored, from wormholes to rotating black holes, Hawking essentially concluded that while the math might allow them, the universe likely has a way of slamming the door shut. He suspected that any attempt to create a time machine and form a closed time-like curve would inevitably trigger a feedback loop of unstoppable energy that would destroy the mechanism before it could ever be used. The proposed enforcer of this cosmic rule is the quantum vacuum. Empty space, according to quantum field theory, is not truly empty. It's a seething, bubbling foam of virtual particles constantly popping into and out of existence. These are particle-antiparticle pairs that borrow energy from the vacuum for an impossibly brief moment before annihilating each other and paying the energy back. Under normal circumstances, this quantum frenzy is invisible and harmless, but near the mouth of a nascent wormhole or the event horizon of a black hole, the extreme warping of space-time can radically alter this delicate dance. Hawking's own work showed how a black hole's gravity can tear these virtual pairs apart, with one particle falling in and the other escaping as radiation. This is the famous Hawking radiation. Now, apply that same quantum ferocity to the throat of a wormhole that is on the verge of becoming a time machine. As the wormhole is tuned to connect 2 points in time, the energy density of these quantum fluctuations is predicted to skyrocket to infinity. An unstoppable flood of particles and radiation would erupt, creating a feedback loop of unimaginable energy that would vaporize the wormhole or whatever structure you are using in an instant. It wouldn't just be a catastrophic failure, it would be a physical imperative. The laws of quantum mechanics would literally conspire to generate an infinite amount of energy to prevent the paradox of a closed time-like curve from ever forming. The universe, in this view, is not merely indifferent to time travel. It is actively hostile to it, equipped with a fundamental failsafe that makes altering the past a physical impossibility. Hawking, ever the scientist with a sharp wit, decided to put this idea to a clever, if informal, test. He held a party for time travelers. The invitation was issued only after the party had already concluded. He set out champagne and snacks and waited, hoping that someday a future time traveler would use their technology to come back and attend. He even sat there alone for a while, just in case. Crucially, he only sent the invitations out after the party's scheduled time had passed, ensuring that only someone who could travel backward in time would ever know about it. The result: no one showed up. For Hawking, this was amusing but compelling anecdotal evidence that time travel to the past is simply not possible. If it were, he reasoned, surely someone in the future would have heard of his famous experiment and taken the opportunity to prove him wrong. The empty room stood as a silent testament to his conjecture, a universe where the past is and must remain immutable. So if Hawking's conjecture paints a picture of a universe that actively guards its history, what if the key to time isn't hidden in the vastness of space, but in the creation of entirely new forms of matter? This brings us to one of the most revolutionary and bizarre concepts in modern physics: time crystals. First proposed by Nobel laureate Frank Wilczek in 2012, this idea challenges one of our most fundamental assumptions, that stable matter exists in its lowest energy state, at rest. A time crystal is a theoretical and now experimental object that does the impossible. It moves in a stable, repeating cycle without any energy input. It's a structure that has broken not just spatial symmetry, like a standard crystal with its repeating atomic lattice, but time symmetry as well. To grasp this, imagine a standard crystal like a diamond. Its atoms are arranged in a repeating pattern in space. It's symmetrical because if you shift your perspective by a specific amount, the structure looks the same. A time crystal exhibits this same kind of regularity, but in the dimension of time. Its internal structure oscillates or rotates in a periodic cycle that repeats at a set interval forever without slowing down or losing energy. It's not a perpetual motion machine that creates energy from nothing, which would violate thermodynamics. Instead, it's a system already in its ground state that nonetheless displays motion. It's like a clock that ticks eternally without ever being wound, or a ring of atoms that forever rotates without friction. This perpetual oscillation is its natural, lowest energy state. The implications for our understanding of time are profound. In physics, most laws are time-symmetric. They work the same whether time runs forward or backward. But the universe we experience has a definite arrow of time moving from past to future. Time crystals represent a system that spontaneously breaks this symmetry, choosing a preferred rhythm in time. This makes them a unique laboratory for studying the nature of time itself. If we could learn to control and manipulate these cycles, could we find a way to imprint information onto this temporal structure, or even use it to create a stable reference frame for timekeeping of unimaginable precision? The most astonishing part is that time crystals have moved from wild theory to laboratory reality in a remarkably short period. In 2017, two separate teams of researchers, one at the University of Maryland and another at Harvard, successfully created time crystals in controlled experiments. They didn't use magical materials. They used complex systems like chains of ytterbium atoms or diamonds with dense nitrogen vacancies. The researchers would kick the system with a laser pulse, initiating the oscillation. According to classical physics, the system should eventually settle down, but in these quantum systems, the atoms responded by settling into a stable, repeating rhythm that was a different frequency than the laser's pulse. They had found a new, stable state of matter that was ticking along in its own personal time, resistant to external disturbances and entropy. This was a monumental validation of a once controversial idea. While we are a universe away from building a time machine from time crystals, their most immediate and powerful application lies in the realm of quantum computing. One of the biggest hurdles for quantum computers is decoherence, the tendency for fragile quantum states to collapse from the slightest environmental interference, erasing the information they hold. The inherent stability and periodic motion of time crystals could provide a protected, coherent state to store quantum information, acting as a perfect, self-correcting quantum memory that is resistant to external noise. This could be the breakthrough needed to scale up quantum computers from fragile experiments to powerful, practical machines. And it is perhaps in this role, as a component of unimaginably powerful quantum computers, that time crystals might indirectly open a door to time manipulation. A quantum computer capable of simulating the universe in incredible detail could model the effects of closed time-like curves or the stability of wormholes with far greater accuracy than ever before. It could run simulations that test the limits of causality and chronology protection in ways our current math cannot. The time crystal, a device that has mastered a form of perpetual motion in time, could become the heart of a machine that allows us to finally run the equations to truly understand time's deepest secrets, not by bending space-time with gravity, but by harnessing the strange, silent ticking of matter itself. But if we step back from the mechanics of machines and particles, we are forced to confront a much deeper question about the nature of time itself. What if the past, present, and future aren't fleeting moments that come into being and then vanish, but are all equally real, existing together in a single, unchanging structure? This is the core idea behind the block universe theory, a view of reality that emerges directly from Einstein's own work and presents a cosmos that is both elegantly simple and philosophically staggering. In this model, the entire universe, every event that has ever happened or ever will happen, is frozen together into a single four-dimensional block. The three dimensions of space and the one dimension of time are all laid out together, with no single moment having any special status as the now. Your birth, your first day of school, your reading of this sentence, and every moment of your future are all just fixed locations within this vast, unchanging structure. From a God's eye view outside the block, the whole tapestry of history is visible at once. This isn't a far-fetched idea. It's the most natural interpretation of Einstein's relativity, where the experience of a flowing now is relative to each observer. There is no universal present. This framework completely reframes the concept of time travel. In a block universe, you wouldn't be changing the past or creating a new future. Those ideas are meaningless because the past and future are just as real and unchangeable as a distant mountain is in space. Time travel would simply be the process of moving your consciousness from your current coordinates in the four-dimensional block to another set of coordinates. It would be like moving from one room in a vast mansion to another. The room you left and the room you're going to both exist simultaneously. You're just changing your location within the structure. A time machine, in this view, wouldn't be a history-altering device but a kind of cosmic transporter, moving you along the temporal axis to a point that has always been there. This leads us directly to one of the most profound and unsettling implications of this theory, the question of free will. If the entire future is already written into the block, fixed and unalterable, then do our choices truly matter? It can feel like our lives are reduced to a pre-recorded movie that we are merely watching unfold, with our sense of decision-making being nothing more than an illusion. The you that will choose oatmeal tomorrow instead of toast isn't making a choice. That event is simply a permanent fixture in the cosmic landscape, as predetermined as the orbit of Jupiter. This deterministic view can feel deeply disempowering, suggesting that our struggles, our triumphs, and our regrets were all encoded into the universe at its inception. However, many philosophers and physicists argue that this is a misinterpretation. They suggest that the block universe doesn't eliminate free will, it simply incorporates it. Your choices are real, and they have real consequences. It's just that those choices and their consequences are eternally part of the universal block. The future is fixed precisely because you will freely make those choices. The you in the future isn't being forced to choose oatmeal. That future, you freely selects it, and that free action is what becomes a permanent part of the cosmic record. In this view, the block universe is not a prison but a biography, a complete account of every free action that ever occurs. This perspective allows for free will and determinism to coexist. The story is written, but we are the authors writing it with every decision we make. This makes the idea of time travel possible, but perhaps less exciting than our science fiction dreams. There would be no danger of paradox because every event is locked into its relationship with every other event. You could not go back and kill your grandfather because the block universe already contains the fact that you did not do that. If you appear in the past, it's because you were always there. Your journey is just a part of the overall, consistent timeline. You might be able to witness historical events, but you could never change them. The appeal of time travel often lies in the power to alter outcomes and fix mistakes, but in a block universe, those mistakes and their consequences are just as permanent and real as everything else. You could visit them, but you could never erase them. The universe, in this view, is a perfect, immutable tapestry, and time travel is merely the ability to look at a different part of the weave. Building on the idea of using immense rotation to twist time into a loop, we encounter one of the most mathematically elegant yet physically improbable solutions to Einstein's equations, the Van Stockum dust cylinder. Proposed by Dutch mathematician Willem Jacob van Stockum in 1937, this model takes the concept of frame dragging and pushes it to an absolute extreme, creating a time machine from what seems like the most mundane of substances, dust. But this isn't the dust you find on a bookshelf. It's a theoretical, infinitely long cylinder composed of a perfectly symmetrical cloud of dry, non-interacting particles, all rotating in perfect unison around a common axis. The sheer collective momentum of this spinning dust creates a gravitational vortex so powerful that it doesn't just drag space-time around with it, it ties time itself into knots. To visualize how this works, imagine stirring a cup of tea with a spoon. The liquid closest to the spoon spins the fastest, caught in its immediate gravitational pull, creating a whirlpool. Now replace the spoon with an infinitely long cylinder of dust, spinning at a significant fraction of the speed of light. The dust particles themselves are the source of the gravity that shapes the space-time around them. As this colossal cylinder rotates, it grips the fabric of the universe and pulls it along, much like the spoon pulls the tea. This is frame dragging, but on a scale so intense that the paths objects can take through space-time become fundamentally altered. Close to the cylinder, the dragging is so violent that the direction of future is no longer pointed forward in time. It is literally twisted around the cylinder, forced into a loop. A spacecraft traveling on a carefully chosen path around this spinning dust cloud could find itself on a trajectory that circles back to its own past, creating a closed time-like curve. You wouldn't be moving faster than light. You'd simply be riding the whirlpool of distorted time, following a road that has been coiled into a circle by the sheer rotational force of the dust. The incredible part of Van Stockham's work is that this isn't just a fanciful idea. It is an exact, mathematically rigorous solution to Einstein's field equations of general relativity. It demonstrates with crystal clarity that the laws of physics as we currently understand them do not inherently forbid time travel. The geometry of the space-time around this cylinder is so warped that the timeline, the very sequence of cause and effect, is wrapped around the cylinder like a helix. For an observer far from the cylinder, time flows normally, but for an observer navigating this twisted region, the future and the past connect, forming a loop without a beginning or an end. It's a profound demonstration that the universe's rulebook might allow for journeys into the past under very specific, albeit wildly unrealistic conditions. However, the beauty of the mathematics is matched only by the staggering implausibility of building such a structure in reality. The model comes with a set of requirements that are so extreme they effectively place this time machine in the realm of pure theory. The first and most obvious problem is the cylinder itself. For the solution to hold true and create stable closed time-like curves, the cylinder must be infinitely long. Constructing an object of infinite length is, to put it mildly, a rather significant engineering challenge that lies entirely beyond any conceivable technology. The second monumental hurdle is the composition of the cylinder. It must be made of this dust, a term physicists use to describe a perfect, pressureless fluid where the particles do not collide or interact with each other in any way. They must simply orbit the axis in perfect, silent harmony, their collective gravity doing all the work. Finding or creating a substance that behaves with such perfect, idealized simplicity is impossible. All real matter interacts, collides, and generates pressure and friction, which would disrupt the delicate balance required for the effect. Furthermore, the entire system demands absolute perfection. Any tiny imperfection in the symmetry of the cylinder, any small lump or irregularity in the density of the dust, would likely destabilize the delicate space-time geometry, causing the closed time-like curves to collapse or never form at all. The universe is a messy, chaotic place, and the Van Stockham dust cylinder requires a level of precision and order that is utterly unattainable. So, while this solution stands as a brilliant testament to the power of general relativity and a fascinating clue that time travel might be mathematically possible, it also serves as a reminder of the vast gulf that often exists between a beautiful equation on a page and the gritty, imperfect reality of the physical cosmos. It is a time machine that could only ever exist in the pristine world of theory, a ghostly blueprint for a journey to the past that the universe's own messy nature seems designed to prevent. Yet for all the grand cosmic machines we've imagined, from spinning cylinders to warping spacetime, there remains a fundamental problem that has vexed physicists for nearly a century. Einstein's General Relativity gives us a breathtakingly accurate picture of the universe on the largest scales, describing the graceful dance of planets, stars, and galaxies through curved spacetime. Meanwhile, quantum mechanics provides an equally powerful, though utterly bizarre, set of rules that govern the subatomic world of particles and probability. The trouble is, these two monumental pillars of modern physics are fundamentally incompatible. They speak different mathematical languages and describe reality in mutually exclusive ways. This great schism becomes most apparent in places where both gravity and quantum effects must be considered simultaneously, at the center of a black hole or the moment of the Big Bang. To truly understand time, and to see if time travel could ever be more than a theoretical curiosity, we must find a theory that can unite these two domains. This is the holy grail of modern physics, the quest for a theory of quantum gravity. One of the most promising and deeply fascinating candidates in this quest is loop quantum gravity, or LQG. Unlike string theory, which proposes that the fundamental building blocks of the universe are tiny, vibrating strings, loop quantum gravity takes a more direct approach. It asks a profoundly simple question: what if spacetime itself is not smooth and continuous as Einstein described, but is actually made of something? What if it has a discrete, granular structure, much like a piece of fabric is woven from individual threads? LQG proposes that on the smallest possible scale, at the so-called Planck length of about 1.6 times 10 to the negative 35 meters, spacetime is not a seamless continuum. Instead, it is woven from an incredibly dense, network-like structure of tiny, one-dimensional loops. These loops are the elementary quanta of space itself, the individual pixels that make up the screen of our reality. This radical idea of a granular spacetime has a stunning implication for the nature of time. In LQG, time is also quantized. It does not flow like a river, but rather advances in the tiniest, discrete steps, like the second hand on a clock, but ticking at a rate of about 10 to the 43 times per second. Between one Planck time and the next, there is no in-between. This discrete structure could potentially resolve the monstrous infinities that plague our current theories, particularly the singularity at the heart of a black hole. In Einstein's relativity, the center of a black hole is a point of infinite density where the laws of physics break down completely. But in the framework of loop quantum gravity, there is a limit to how tightly space can be compressed. The network of loops gets squeezed to its maximum density and then, according to the math, can actually spring back in a tremendous rebound. This suggests that a black hole singularity might not be an ultimate end, but a bridge, a quantum tunnel to another part of the universe or even another universe entirely. This is where the concept of time travel re-enters the picture in an entirely new microscopic form. If the fabric of spacetime is a pliable network of loops, then perhaps it's possible for these threads to be woven into structures that connect different points in time. The extreme conditions at the center of a black hole, or those that existed during the Big Bang, might naturally twist this quantum weave into a tunnel, a wormhole that exists not on a cosmic scale but at the Planck scale. These wouldn't be the giant, stable tunnels you could fly a spaceship through. They would be ephemeral, quantum-sized shortcuts flickering in and out of existence in the foam of spacetime. To travel through one, you wouldn't need a machine in the traditional sense. You would need a way to somehow harness these quantum effects, to enlarge and stabilize one of these natural tunnels, or perhaps to encode information onto a particle and send it through. It's a vision of time travel that is less about engineering and more about mastering the deepest, most fundamental language of the universe. Of course, this remains one of the most speculative frontiers of physics. We are nowhere near being able to probe or manipulate spacetime at the Planck scale. It is over a billion times smaller than a proton. The energies required are orders of magnitude beyond what any particle collider could ever hope to achieve. Furthermore, loop quantum gravity is just one of several competing theories vying to be the theory of quantum gravity. And while its mathematics are elegant and its solutions for resolving singularities are compelling, it is not yet a complete or experimentally verified framework. It offers a breathtakingly beautiful possibility that the key to unlocking time might not be found in the vastness of space, but in the intricate, woven tapestry of reality itself, waiting to be read in the loops and knots of quantum geometry. From the granular loops of quantum gravity, we now expand our view to a theory that proposes reality is woven from even more fundamental threads. This brings us to one of the most ambitious and mathematically complex frameworks in all of physics, string theory. At its heart, string theory offers a simple yet radical swap. Instead of point-like particles, the universe's most basic ingredients are unimaginably tiny, vibrating strings. Just as a single violin string can vibrate at different frequencies to produce a multitude of distinct musical notes, these fundamental strings vibrate in different modes. One particular resonant pattern might manifest as an electron, while another different vibration gives rise to a photon, a quark, or the gravitational force itself. This elegant idea promises to be a true theory of everything, seamlessly unifying all forces and matter under a single mathematical umbrella. But this breathtaking unification comes with a fascinating and necessary requirement. The universe must have more than the three spatial dimensions we experience every day. For the complex mathematics of string theory to work consistently, it demands a reality of 10, or in some versions, 11 dimensions. We are comfortable with length, width, and height, and we experience time as a fourth dimension. So where are the other 6 or 7? The theory posits they are compactified or curled up into an astonishingly tiny space at every single point in our familiar cosmos. Imagine a long, thin garden hose stretching off into the distance. From far away, it looks like a simple one-dimensional line. But if you were an ant crawling on its surface, you would discover a second dimension, the circular dimension curled around the hose's circumference. String theory suggests our reality is like that hose. At every point we can see, there are 6 additional spatial dimensions curled up into a complex, multi-dimensional shape called a Calabi-Yau manifold, a structure so small that it's completely hidden from our everyday perception. This higher dimensional landscape is where the potential for time travel enters the picture, and it does so through the concept of brains, short for membranes. Brains are dynamic objects that can exist in multiple dimensions. Our entire universe, with its 3 dimensions of space and 1 of time, could be a 3-brain, a 3-dimensional membrane floating within a higher dimensional bulk space. Other brains with different numbers of dimensions could also exist in this bulk, perhaps even hosting their own separate universes with completely different physical laws. This opens up a staggering possibility. If our universe is a brain, then moving through the higher dimensional bulk could allow for shortcuts that completely bypass the normal constraints of our 4-dimensional spacetime. To visualize this, think of 2 cities on opposite sides of a mountain. Traveling between them along the winding roads on the mountain's surface within our brain is a long and arduous journey. But if you could burrow a tunnel directly through the mountain through the higher dimensional bulk, you would create a dramatically shorter path. In the context of time, such a bulk shortcut could connect not just distant points in space, but distant moments in time. By moving our brain through the bulk, or by finding a way to slide an object from one point on our brain to another through the bulk, we might effectively leapfrog across the timeline. A journey that would take billions of years at the speed of light within our brain could be instantaneous through the bulk, functioning as a form of time travel to the future. More speculatively, if the geometry of the bulk allows for complex loops, it might even permit travel to the past. The challenge, of course, is as immense as the idea is compelling. Those extra dimensions are not just hidden, they are thought to be curled up at the Planck scale, a size so vanishingly small that accessing them directly is, with our current understanding of physics, utterly impossible. We would need energies beyond comprehension to uncurl a dimension or to puncture a hole from our brain into the bulk. It would be like a drawing on a piece of paper trying to reach out and manipulate the artist holding the pencil. We are confined to the surface of our own reality. Furthermore, the mathematics of string theory, while elegant, is notoriously difficult and produces a vast number of possible solutions. A landscape of potential universes, estimated to be around 10 to the 500th power in number. Finding the one solution that precisely describes our universe, and within it, a stable method for bulk travel, is like finding a single unique grain of sand on every beach on Earth. So while string theory provides a mathematically rich and captivating playground for imagining how time travel could be woven into the very fabric of reality, it remains, for now, a beautiful and untested symphony of equations, a potential key to the cosmos that we have not yet learned how to turn. But if we are living in a universe fine-tuned for our existence, what does that say about the possibility of time travel happening all around us, hidden in plain sight? This brings us to a fascinating intersection of cosmology and speculation known as the anthropic principle, and its profound implications for our journey through time. In its simplest form, the anthropic principle observes that the universe we observe must be compatible with our existence as conscious observers. The fundamental constants of nature, the strength of gravity, the mass of an electron, the force binding atoms, appear exquisitely fine-tuned. If any of them were even slightly different, stars wouldn't form, complex chemistry would be impossible, and life as we know it could never arise. This has led to a compelling thought. Perhaps there are a multitude of universes, a vast multiverse, each with its own unique set of physical laws. We find ourselves in this one not because it's special, but because it's one of the rare ones where conditions are just right for us to be here to ask the question. Now apply this reasoning to time travel. The theoretical pathways we've explored, from wormholes to closed time-like curves, often come with a terrifying threat: the potential for universe-breaking paradoxes. The grandfather paradox is the classic example, a logical inconsistency that seems to make time travel to the past an impossible fantasy. But the anthropic principle offers a different, almost soothing resolution. It suggests that if time travel is possible at all, then we must necessarily live in a universe where its use does not lead to such catastrophic paradoxes. Our very existence is proof that the timeline is stable and self-consistent. Any attempt to create a paradox would simply fail, not because of a universal law against it, but because if it succeeded, we wouldn't be here to witness it. The universe we observe is one where time travel, if it occurs, is either impossible or happens in a way that is completely consistent with the history that led to our arrival. This leads to two equally intriguing possibilities. The first is that time travelers are already among us, but they are constrained by a kind of prime directive, a set of rules or a simple necessity to remain hidden. Their very presence must not disrupt the chain of events that allows their own civilization to eventually develop time travel technology. A tourist from the future couldn't step on a butterfly and accidentally prevent their own birth, so their excursions into the past would have to be meticulously planned acts of observation, leaving no detectable trace. They would be the ultimate historians, forbidden from interacting, their technology designed to be perfectly invisible. This could explain the Fermi paradox for time travel. If they are here, where are all the time tourists? The answer might be that they are flawless spectators, their advanced technology making them undetectable to our primitive senses and instruments. The second possibility is even more profound. that history is not fragile but incredibly resilient. The web of cause and effect might possess a kind of immune system, an inherent stability that absorbs changes and self-corrects. A time traveler attempting to alter a major event might find that their actions are simply incorporated into the historical record, always having been a part of what actually happened. Perhaps the reason we have no evidence of time travelers is that their attempts to change the past are what created our present in the first place. Every anomaly in history, every mysterious stranger who appeared at just the right moment, every piece of lost technology that seems out of place, could be a subtle signature of their activity, an activity that is fundamental to the timeline itself, not an alteration of it. Our universe, selected by the anthropic principle, is one where the past is not a dry history book to be edited, but a living, breathing, and shockingly robust structure that has already accounted for every possible intervention, ensuring that the story always leads to us. But what if the ultimate time machine wasn't a device you built, but a type of universe you could simply visit? This leads us to one of the most intellectually staggering concepts in all of theoretical physics, Malamute-Hogarth spacetimes. These are not machines or particles, but entire cosmic geometries, specific solutions to Einstein's equations, where the very fabric of reality is arranged to make an infinite amount of time accessible within a finite personal experience. It's an idea that challenges our deepest intuitions about duration, knowledge, and the limits of what is possible. To grasp this, imagine two observers embarking on a journey in a specially constructed universe. The first observer, let's call them the traveler, sets off on a path that will take them on a finite, subjective journey. From their perspective, only a limited amount of time passes, say, 10 years. The second observer, the witness, remains in a stationary position. Due to the extreme and specific warping of space-time in a Malamute-Hogarth universe, the traveler's 10-year journey coincides with an infinite amount of time passing for the witness. When the traveler returns after their decade-long trip, the witness has, from their perspective, experienced eternity. The entire future history of the universe, an infinite progression of events, has unfolded before the stationary observer's eyes. This bizarre scenario becomes a powerful engine for computation and knowledge. Consider the famous halting problem in computer science, which states that there is no general algorithm that can determine, in a finite amount of time, whether any given computer program will eventually stop running or loop forever. In our normal universe, this is an unsolvable problem for an infinite number of cases, but in a Malamute-Hogarth spacetime, you could defeat this limit. You could give the witness a computer program of infinite complexity and instruct them to run it. The traveler then embarks on their journey. For the traveler, only 10 years pass. When they return, they meet the witness for whom an infinite amount of time has elapsed. The witness would have had all the time in the world, literally, to run that program to completion and discover its answer. The traveler could then simply ask, "Did it halt?" and receive a definitive yes or no answer to a question that is fundamentally unanswerable within any finite time frame in our universe. This principle extends beyond computation to communication. A Malamute-Hogarth geometry could serve as the ultimate messaging system. Imagine you want to send a message to the infinite future. In this spacetime, you could dispatch the traveler on their finite journey. The witness, experiencing infinite time, could spend eons compiling the sum total of all knowledge, the answer to every question, the entire history of everything that ever will happen. When the traveler returns after their short trip, the witness could hand them this ultimate encyclopedia, a message from eternity. The traveler would then possess infinite knowledge, all gained in a finite amount of their personal time. The burning question, of course, is whether our own universe permits such mind-bending geometries. The mathematical models for Malamute-Hogarth spacetimes often involve incredibly extreme conditions, such as the regions near certain types of naked singularities or within the elaborate structures of rotating Kerr black holes that we discussed earlier. However, most physicists believe that various cosmic censorship hypotheses, rules the universe might enforce, prevent such geometries from forming in a stable, accessible way. The intense energies and infinite curvatures involved would likely be shielded by event horizons or would collapse under their own instability, protecting the causal order of the universe from the logical chaos that unfettered time travel could unleash. Our cosmos seems to have guardrails in place that prevent these infinite time loops from being practically utilized, suggesting that while Malamute-Hogarth spacetimes are a breathtaking feature of Einstein's mathematical universe, they are probably not a ticket to infinite knowledge that we can ever punch. As we venture from the mind-bending geometries of Malamute-Hogarth universes back to the fundamental forces shaping our own cosmos, we encounter a mystery that is both everywhere and nowhere, an invisible driver of cosmic destiny that might hold unexpected power over time itself. This brings us to one of the most profound and puzzling discoveries in modern cosmology: dark energy. In the late 1990s, astronomers made a shocking observation. By measuring the light from distant supernova, they found that the expansion of the universe isn't slowing down, as everyone had assumed, due to the collective gravitational pull of all matter. Instead, the expansion is accelerating. Galaxies are flying apart from each other at a faster and faster rate, as if some unseen repulsive force is stretching the very fabric of spacetime itself. This mysterious energy causing the acceleration was dubbed dark energy, and it makes up a staggering 68% of the total energy content of the universe. Yet, we have no idea what it actually is. The leading candidate for dark energy is the cosmological constant, a concept first proposed by Einstein himself and later called his greatest blunder. In his equations of general relativity, Einstein included a fudge factor represented by the Greek letter lambda, to allow for a static universe that wasn't collapsing under its own gravity. When the universe was discovered to be expanding, he discarded the idea. But now, lambda is back with a vengeance, as it perfectly describes a constant energy density inherent to the vacuum of space itself. Think of empty space not as truly empty, but as a seething quantum foam where virtual particles flicker in and out of existence. This constant activity endows every cubic centimeter of nothingness with a tiny, non-zero energy. Across the vastness of the entire cosmos, this vacuum energy adds up to an immense force that pushes spacetime apart, causing the accelerated expansion we observe. This is where the connection to time becomes tantalizingly speculative. In general relativity, the curvature of spacetime is directly linked to the flow of time. We've already seen how massive objects like planets and black holes create gravity wells that slow time down in their vicinity. Dark energy operates on the opposite principle. It creates a kind of negative pressure or repulsive gravity that stretches spacetime. So, could we somehow manipulate this dark energy to affect time locally? Imagine if we could create a device that could concentrate or focus this vacuum energy in a specific region. In an area of intensified dark energy, the repulsive effect would be stronger, causing spacetime to expand at a much more rapid rate relative to its surroundings. According to relativity, this accelerated expansion would directly influence the passage of time within that bubble. An observer inside might experience time flowing at a normal rate, but from the outside, their timeline would appear drastically sped up. You could step into such a field for what feels like a few minutes and step out to find that years had passed in the outside world. A method for leaping into the future that relies on manipulating the vacuum of space itself rather than traveling at relativistic speeds. The challenges, of course, are as monumental as the concept is fascinating. First, we don't know how to interact with dark energy at all, let alone control it. It appears to be perfectly uniform and uniforming, permeating all of space with no local variations we can latch onto. It doesn't clump like matter, it seems to be a property of space itself. Second, the energy density of the vacuum, as predicted by quantum field theory, is astronomically higher by a factor of 10 to the 120th power than what we observe from the cosmological constant. This cosmological constant problem is one of the greatest unsolved mysteries in physics, until we can reconcile why the vacuum energy is so much weaker than it should be. The idea of manipulating it remains a distant dream. Furthermore, concentrating such energy might require exotic matter with negative energy density, the same mysterious substance needed to stabilize wormholes, pushing this idea deep into the realm of speculative physics. Yet the potential is staggering. Mastering dark energy wouldn't just be about understanding the fate of the universe. It could be the key to building a machine that controls the very rate of time's flow. But if manipulating dark energy feels like trying to bend the universe to our will, perhaps a more subtle approach lies in the strange, silent language of the quantum world itself. This brings us to a concept that sounds like it's straight out of science fiction, but is actually a proven laboratory reality: quantum teleportation. However, this isn't the Star Trek style of teleportation where a person is disassembled here and reassembled there. Instead, it's the teleportation of information, the precise quantum state of a particle. And while we use it to send data across space, its deepest implications might just rewrite our understanding of communication across time. At the heart of this process is the spooky phenomenon of quantum entanglement. We create a pair of particles whose fates are linked so intimately that measuring one instantly determines the state of the other, no matter the distance separating them. To teleport the quantum state of a third particle, we perform a special kind of measurement that entangles it with one half of our prepared pair. This measurement destroys the original state of our target particle, adhering to the quantum no-cloning theorem, which states you can't copy an unknown quantum state, but it also produces a classic, ordinary piece of information, a 2-bit code. This code is then sent the old-fashioned way, at light speed or slower, to the receiver holding the other half of the original entangled pair. Upon receiving this code, the receiver performs a specific operation on their particle. Miraculously, their particle is now in the exact quantum state that the original particle was in before it was measured. The information hasn't traveled faster than light. The spooky connection of entanglement facilitated the transfer, while the classic signal provided the final instructions to complete the reassembly. Now, let's twist this concept from the spatial to the temporal. What if we could establish entanglement not between 2 points in space, but between 2 moments in time? This is the radical idea of temporal teleportation. Instead of having 2 entangled particles separated by a kilometer, imagine creating a pair of particles that are entangled across time. You could entangle a particle in your lab today with a particle that will exist in your lab tomorrow. If this were possible, the same teleportation protocol could, in theory, be used to send quantum information into the future. You would perform the measurement on your particle today, send the classic 2-bit code to the future lab via a normal signal, and the scientist there could use it to reconstruct the quantum state you had 24 hours prior. You haven't sent matter back in time, but you have sent its most fundamental blueprint, its quantum identity, forward to a specific point in time for reconstruction. The far more speculative and paradigm-shifting possibility is doing this in reverse, sending quantum information into the past. This would require entanglement with a particle that already existed at a previous moment. If you could somehow entangle a particle now with a particle that existed a day ago, you could potentially teleport a quantum state backwards in time. The measurement you make today would instantly affect the state of the historical particle, and a classic signal sent into the past, which is, of course, its own impossible problem, would provide the key for a receiver in the past to complete the teleportation. This idea violently clashes with our classical understanding of cause and effect, suggesting that an effect in the present could reach back and influence a cause in the past. While this seems to invite paradox, some interpretations of quantum mechanics, particularly those involving retrocausality, suggest that the universe's quantum rules might allow for such backward-in-time influence without creating logical inconsistencies, as the events would remain statistically self-consistent across the timeline. The most formidable obstacle to this entire idea is the no-cloning theorem, a fundamental law of quantum mechanics that states it is impossible to create an identical, independent copy of an arbitrary, unknown quantum state. This is why the original particle state is destroyed during teleportation. You can't have two copies. For time travel, this presents a fascinating constraint. You couldn't simply make a copy of yourself in the past because your complete quantum state is impossible to clone. However, teleportation circumvents this by moving the state rather than copying it. So, in a temporal teleportation scenario, you might be able to reconstruct your quantum state at a different time, but the you in the present would cease to exist in that original form, having been measured and effectively disassembled. This isn't cloning, it's relocation across time. Your consciousness, your very pattern, would be reassembled in the past or future, but it would be a continuation, not a duplication. This provides a potential, though wildly speculative, mechanism for personal time travel that respects the universe's deepest laws against copying, turning the no-cloning theorem from a barrier into the very rule that would make such a journey a one-way, all-or-nothing proposition. But this idea of a self-correcting, self-fulfilling timeline isn't just a clever narrative device for science fiction. It finds a strange and unsettling echo in our own world through the principles of chaos theory. Often summarized by the so-called butterfly effect, chaos theory reveals that in complex, interconnected systems, a tiny, seemingly insignificant change can ripple outward and produce enormous, unpredictable consequences. A time traveler stepping on a single butterfly in the prehistoric past could, in theory, set off a chain of events that dramatically alters the future. The predestination paradox takes this a step further. It suggests that the timeline isn't just sensitive to change, it's actively resilient against it. The universe of cause and effect might possess a kind of inertia, a preferred path that incorporates any attempt at intervention, no matter how well-intentioned, back into the original, unchangeable story. Your attempt to prevent a war might be the very spark that ignites it. Your warning about a disaster might be the reason no one heeds the true signs. In this view, free will and fate are not in opposition. They are dancing partners in a choreography that was always meant to be, where our choices are genuine, but their ultimate outcome is preordained within a closed, immutable loop. The paradox isn't a flaw in time travel. It's a feature of a universe that demands consistency, ensuring that every event, including the journey to stop it, finds its necessary and permanent place in the tapestry of history. Now we enter a realm of time travel that feels less like physics and more like a mesmerizing and maddening riddle, a puzzle where the answer and the question chase each other in an endless, originless loop. This is the bootstrap paradox, a concept that doesn't just challenge our technology, but our very understanding of where things come from. Imagine a struggling composer in 19th century Vienna on the verge of giving up on his dream. One night, a strange, shimmering figure appears in his study, hands him a beautifully bound book of sheet music, and vanishes. The composer, astonished, reads the music and is blown away by its genius. He publishes it under his own name to immediate and everlasting acclaim, becoming the most celebrated musician of his era. The symphony is performed for decades, its melodies echoing through concert halls. Centuries later, a huge fan of this very symphony, who also happens to be a time traveler, decides to go back in time to meet his hero. As a gift, he brings a first edition copy of the famous symphony. He arrives, finds the young composer before his rise to fame, and hands him the book of music before disappearing back to his own time. So, who really composed the symphony? It has no true origin. It was never created by anyone. It simply exists trapped in an infinite loop, each iteration causing the next. The information is its own cause and its own effect, a closed circle of existence with no beginning and no end. This paradox gets its name from the absurd idiom of pulling yourself up by your own bootstraps, an impossible task where you try to lift yourself off the ground by tugging on your boots. The object or piece of information in the loop has no independent point of creation. It is completely self-contained and self-referential. It's not just a piece of music, it could be a physical object. Imagine a robot that is sent back in time with the blueprints for its own construction. Scientists in the past used these flawless blueprints to build the very same robot, which is then later sent back in time with its own blueprints. The design for the robot, its intricate schematics and complex AI, never had an inventor. The knowledge to create it was never developed through research, trial, and error. It was always just there, an eternal puzzle waiting to be assembled over and over again. From a purely physical standpoint, if closed time-like curves are possible, then the bootstrap paradox isn't just a fun thought experiment. It becomes a genuine, allowable outcome. The laws of physics, as described by General Relativity, might not care about where something came from, only that the timeline is consistent. If an object's world line forms a closed loop, the universe's math might be perfectly happy with that. There's no law of conservation of origin. The object's energy and mass are conserved within the loop. It doesn't pop into existence from nothing at any single point. It's always traveling, its existence spread out across the entire loop. The paradox is purely an informational and causal one, a problem for our human minds that are hardwired to believe every effect must have a cause that came before it. This is where the bootstrap paradox strikes at the heart of our understanding of creativity and existence itself. It forces us to ask, does everything need an origin story? If a beautiful painting exists in a loop, is it any less beautiful because we can't point to the artist who first conceived it? The value isn't diminished, but our ability to understand its history is completely unraveled. It creates a universe where things can simply be, without a creator, without a first cause, eternally present in the timeline. This idea is deeply unsettling because it removes agency and ingenuity from the equation. Human progress is built on the idea of standing on the shoulders of giants, of each generation building upon the discoveries of the last. The bootstrap loop obliterates that. It's a closed system of knowledge where nothing new is ever truly created. Things are only ever rediscovered from their own future. In such a universe, the very concepts of innovation and originality would take on a completely different and perhaps far more mysterious meaning. But what if the ultimate journey through time requires no machine, no cosmic shortcut, and doesn't even involve moving your body? What if the key to visiting the past or future lies entirely within the realm of perception and consciousness itself? This leads us to one of the most philosophically daring interpretations of quantum mechanics, the many minds interpretation. This theory takes the bizarre paradoxes of the quantum world and proposes a solution that is both elegant and deeply personal, suggesting that time travel might not be a physical voyage at all, but a shift in the state of your own awareness. To understand this, we first need to revisit the infamous measurement problem in quantum mechanics. In the classic double-slit experiment, a single particle like an electron seems to pass through two slits at once, behaving like a wave and creating an interference pattern. But the moment we set up a detector to see which slit it goes through, the particle suddenly behaves like a single, localized object, and the interference pattern vanishes. The act of observation, of measurement, seems to force the particle to choose a single state. The many minds interpretation, an extension of Hugh Everett's many worlds theory, offers a unique perspective on this. It agrees that every possible quantum outcome does indeed occur, causing the universe to branch. However, it adds a crucial layer. The branching doesn't just happen out in the universe, it happens within the consciousness of every observer. Imagine you are the scientist watching that electron. In one branch of reality, your mind perceives the electron going through the left slit. In another, nearly identical branch, a different state of your mind perceives it going through the right slit. Both events are equally real, and both versions of your conscious experience exist. Your stream of awareness, the you that feels continuous, is actually just one thread of perception weaving through an infinite tapestry of mental states. According to this view, there aren't countless physical universes constantly splitting. There is one vast, undivided quantum universe, but it is teeming with an uncountable number of conscious perspectives, each experiencing their own unique timeline of events. Now, apply this revolutionary idea to time travel. If time travel were possible under the many minds interpretation, it wouldn't involve a machine that moves your physical body to a different year. Instead, it would be a technology or a technique that allows your conscious awareness to jump from your current mental state to a different one, a mental state that is perceiving events from what we would call the past. You wouldn't be physically transported to ancient Rome. Your consciousness would simply shift to a mind state that is experiencing the sights, sounds, and sensations of being in ancient Rome. From your perspective, it would be indistinguishable from real physical travel. You would see the Colosseum, smell the air, and feel the cobblestones under your feet. But your physical body might remain right where it is in the present. You would be an observer, a ghost of perception, experiencing history as it unfolds without ever being able to pick up a stone or speak to a citizen, because you wouldn't actually be there in a physical sense. This framework provides the most elegant solution yet to the problem of paradoxes. Since you are not physically present in the past, you cannot change it. You cannot create a grandfather paradox because you are not interacting with the external world. You are merely tuning your consciousness to observe a different part of the single, unchanging quantum universe. It's the ultimate safe mode for time tourism. You could witness the signing of the Declaration of Independence or watch dinosaurs roam, secure in the knowledge that your presence is purely perceptual and has no causal power to alter the events you are observing. The timeline remains pristine and unchanged while you gain the experience of having been there. This turns time travel from an act of historical intervention into an act of pure enlightenment, a way to satisfy our deepest curiosity without any of the terrifying risks of unraveling reality itself. The implications of this are as profound as they are strange. It suggests that the past and future are not locations to be visited, but are mental states to be accessed. Every moment in history is still happening, not in a parallel universe, but as an available state of awareness within the grand superposition of the quantum world. A time machine, in this sense, would be less like a spacecraft and more like a sophisticated meditation device or a neurological interface that can precisely navigate the infinite landscape of conscious experience. It also raises a deeply personal question. If you could shift your awareness to a mind state perceiving a past event, would you be watching it like a movie, or would you temporarily become the person who was actually there in that time, experiencing their thoughts and emotions? The line between observer and participant, between watching history and reliving it, becomes fascinatingly blurred in a universe where time travel is not a journey through space, but a voyage through the limitless ocean of mind. This idea that information is the true currency of reality brings us to one of the most profound and paradigm-shifting theories in all of modern physics, the holographic principle. To grasp this, we need to venture to the edge of a black hole and confront a terrifying puzzle. When an object falls into a black hole, it vanishes behind the event horizon, seemingly lost forever to our universe. This presents a direct conflict between two cornerstones of physics. General Relativity says the information about that object is destroyed, irretrievably crushed into the singularity. But quantum mechanics insists that information can never be truly lost. It can be scrambled, but it must be preserved in some form. This is the black hole information paradox, a crisis that has troubled physicists for decades. The brilliant resolution, pioneered by physicists like Gerard T. Hooft and Leonard Susskind, is nothing short of revolutionary. They proposed that all the information about every object that falls into a black hole isn't lost inside. Instead, it is perfectly encoded and preserved on the black hole's event horizon, the two-dimensional surface that shimmers around it like a cosmic movie screen. The event horizon is theorized to be made of unimaginably tiny Planck-scale pixels, each storing a single bit of information. The three-dimensional reality of the objects inside the black hole is actually a projection, a hologram, of this two-dimensional data stored on the surface. The black hole's immense interior, with all its contents, is not the primary reality. The flat, encoded data on its boundary is. Now, take this astonishing concept and apply it to the entire cosmos. The holographic principle suggests that our entire universe might operate on the same fundamental rule. The three spatial dimensions we experience, the depth of a room, the height of a mountain, the vast gulfs between stars, may not be fundamental. They could be an emergent secondary reality. The true, fundamental description of our universe might be written on a distant, two-dimensional surface that surrounds us at the unimaginable limit of the observable cosmos. We and everything we see are a magnificent, dynamic holographic projection of that data. We are not living in the real, we are living in the rendered. This has a staggering implication for the nature of time itself. If space is emergent, then time might be as well. In the fundamental, two-dimensional description of the universe, there may be no such thing as time as we experience it. The flow of moments from past to future, the arrow of time, could be a property that only emerges when the data on the boundary is translated into our three-dimensional experience. Time, in this view, is not a fundamental river flowing through the universe. It is more like the perceived motion in a movie, an illusion created by a rapid succession of static frames. The cosmic hard drive at the boundary contains all the frames of history, and our consciousness moves through them, creating the sensation of a flowing present. This radically redefines what time travel could be. You wouldn't need a machine that warps spacetime to journey to the past. Instead, you would need a technology that could access and manipulate the fundamental data on the cosmic boundary. To visit ancient Rome, you wouldn't move your body through time. You would simply call up the data set labeled Rome 80 AD and render it into your experiential reality. You would be immersing yourself in a saved state of the universe. More profoundly, if you had right access to this cosmic hard drive, you could theoretically rewrite history. You could edit the data, changing an event in the past, and that change would then propagate through the entire holographic projection, altering the present and future accordingly. It would be the ultimate act of creation and editing, not by changing events in time, but by updating the source code of reality itself. Of course, the obstacles to such a feat are beyond monumental. The storage capacity required for such a cosmic hard drive is almost beyond imagining. The two-dimensional surface at the boundary of the universe would need to hold approximately 1 bit of information per Planck area, a density that is trillions of times beyond anything we can conceive. Furthermore, we have no idea where this boundary is or how we could possibly interact with it. The technology to read from, let alone write to, the source code of the universe is the stuff of pure, godlike speculation. Yet, the holographic principle remains one of the most active and fertile areas of theoretical physics, not as a blueprint for a time machine, but as a profound new way to understand the very fabric of existence, suggesting that the keys to time itself might not be found in the stars, but in the data that describes them. If black holes are the universe's ultimate one-way streets, swallowing everything that crosses their path, then their theoretical opposites would be cosmic fountains, endlessly pouring matter and energy back out into the cosmos. This is the mind-bending concept of a white hole. In the elegant mathematics of general relativity, the equations that describe a black hole are time-symmetric. This means if you were to mathematically reverse the direction of time in those equations, you would get a white hole. Where a black hole has an event horizon from which nothing can escape, a white hole would have an event horizon from which nothing can enter. It would be a region of space-time that violently expels matter and energy, but that you could never actually reach or enter from the outside. It's as if the universe itself has a severe case of cosmic indigestion, and a white hole is the point where it refuses to take anything else in. This theoretical reversal makes white holes a fascinating candidate for the other end of a wormhole. We discussed earlier how a traversable wormhole would need two mouths. While one mouth could be a black hole relentlessly pulling matter in, the other mouth could be its white hole counterpart, spewing that same matter out somewhere else in the universe or perhaps someone else. In this model, the black hole side would be the entrance and the white hole would be the exit, creating a complete and stable pathway through the cosmos. You wouldn't get spaghettified and crushed at the center. You'd be gracefully ejected from the white hole mouth into a new region of space-time. This offers a potentially safer and more navigable form of travel than trying to brave the chaotic interior of a Kerr black hole, providing a clear and well-defined exit strategy from a cosmic shortcut. The connection to time travel becomes even more profound when you consider the time-reversed nature of a white hole. If a black hole with its immense gravity slows time to a crawl for an outside observer, its mathematical opposite could have the reverse effect. The region around a white hole might experience time at an accelerated rate relative to the rest of the universe. Being near one could be like standing at the mouth of a temporal geyser, where you could watch eons pass in the outside world in what feels like mere moments. Furthermore, if the white hole is indeed an exit from a wormhole, and that wormhole's throat has been manipulated by moving one mouth at relativistic speeds, the white hole exit could open up into a different point in time altogether. You wouldn't just be emerging in a new location, you could be stepping out into a different century. However, there is a monumental reason we have never observed a white hole in nature, and it all comes down to the one fundamental law that does not seem to be time-symmetric, the second law of thermodynamics. This law states that entropy or disorder in a closed system always increases over time. It's the reason why an ice cube melts in a warm room but never spontaneously reforms. It's the arrow of time itself. A black hole is a perfect entropy-increasing machine. It swallows ordered matter, a spaceship, a star, a cloud of gas, and converts it into an incredibly disordered, high-entropy state within its singularity. A white hole would have to do the opposite. It would need to take that incredibly high-entropy, disordered state and spontaneously spew out ordered, low-entropy matter and energy. This would be like seeing a shattered glass suddenly leap off the floor and reassemble itself on the table. It's not mathematically impossible, but it is so astronomically improbable that it effectively never happens in our universe. A naturally occurring white hole would violate the overwhelming statistical preference for increasing disorder, making its existence in the cosmic wild incredibly unlikely. Yet, just because nature might not make them doesn't mean they are entirely impossible. Some physicists speculate that white holes could be created artificially as the eventual end state of a black hole's evaporation. Through the process of Hawking radiation, a black hole slowly loses mass over trillions upon trillions of years. One speculative theory suggests that when a black hole finally evaporates completely, it might not just vanish. Instead, the quantum gravitational effects at its final moment could cause a rebound, a sort of quantum bounce transforming the vanished black hole into a tiny, nascent white hole, briefly pouring the energy of its evaporated mass back out into the universe before disappearing entirely. Furthermore, in some approaches to quantum gravity, like loop quantum cosmology, The Big Bang itself is modeled as a quantum bounce from a previous contracting universe, which can be viewed as a type of white hole event, marking the beginning of our cosmic expansion. So while we may never find a giant white hole floating in space, their imprint might be hidden in the universe's earliest moments or its farthest future, suggesting that even the most outlandish ideas in theoretical physics can find a home in the most profound corners of cosmology. But what if the journey to another time didn't require a tunnel through our own universe, but a leap into an entirely different one? This brings us to a theory that expands the canvas of reality to an almost unimaginable scale, suggesting that our entire cosmos might be just a single bubble in a frothing, infinite sea of creation. This is the concept of eternal inflation and the resulting multiverse. The theory begins in the first fleeting moments after the Big Bang with a field known as the inflaton. Most models have this field settling down, its energy converting into the matter and radiation that fills our universe. But eternal inflation proposes that this process might never truly stop. In this view, the energy of the inflaton field doesn't dissipate evenly everywhere. Think of it like a vast, boiling pot of water. Most areas cool and settle into what becomes a stable universe bubble like our own. But in other regions, the inflationary energy remains incredibly high, causing space to expand at an exponential, faster-than-light rate. This endlessly expanding space becomes the background, the multiverse, while within it, pockets continuously stop inflating and nucleate, forming self-contained bubble universes like our own, each with its own unique set of physical laws and constants. This is where the concept of time travel is completely reimagined. Each of these bubble universes could have its own arrow of time, or perhaps even a completely different experience of time altogether. In one bubble, time might flow in a single, linear direction as it does for us. In another, it might be cyclical, repeating in an endless loop. In a third, the very concept of cause and effect might be reversed, or time might be a two-dimensional entity. Traveling to a different time in this context could simply mean finding a way to cross into a bubble universe where the local, now, corresponds to what we would consider the past or future. You wouldn't be rewriting history in your own timeline. You'd be emigrating to a parallel reality where history unfolded at a different rate or in a different sequence. You could visit a universe that is, from its internal perspective, currently in its own version of the Jurassic period, or one that is experiencing its equivalent of the far future, all while your original home universe continues on its own path completely unchanged. The monumental and likely insurmountable challenge to this form of time travel is the nature of the space between these bubbles. The background multiverse is in a state of permanent, violent inflation, expanding at speeds that forever exceed the cosmic limit of light speed within any stable bubble. This means the space between universes is stretching apart at an uncontrollable, impossible rate. Even if you could somehow puncture a hole in the fabric of our own bubble universe to peer into this chaotic background, the universe next door would be racing away from you faster than any signal, any particle, or any spacecraft could ever hope to pursue. They are causally disconnected islands in a raging sea of nothingness, forever beyond each other's reach. Furthermore, the physical laws that govern the interior of one bubble are likely completely different from those in the next. The moment you try to cross that boundary, your very atomic structure, which is dependent on the specific constants of your home universe, might instantly and catastrophically unravel. Your existence is fine-tuned to the precise physics of your local bubble. Venturing into the inflationary void between them would be like a deep-sea fish trying to survive in the vacuum of space. So while the eternal inflation multiverse offers a breathtakingly vast landscape where every conceivable moment in time is happening somewhere, it also presents a cosmos that seems fundamentally designed to keep its individual residents isolated, forever tantalized by the possibility of other times and places, but forever confined to the unique, beautiful bubble of their own origin. But if accessing another universe feels like an impossible leap, what if the most personal form of time travel doesn't require moving through space at all, but is instead a fundamental feature of your own conscious experience? This leads us to one of the most unsettling and deeply personal ideas at the intersection of quantum mechanics and philosophy: quantum immortality. This concept suggests that from a first-person perspective, your consciousness is essentially incapable of experiencing its own cessation. It's not that you live forever in an absolute sense, but that your subjective experience will always find itself in a branch of reality where you continue to exist, no matter how improbable that survival might seem from the outside. To understand this, we need to revisit the many worlds interpretation, but through a profoundly personal lens. Imagine a drastic and grim thought experiment known as quantum suicide. A volunteer is placed in front of a device that is triggered by a random quantum event, like the decay of a single radioactive atom. In 1 second, there is a 50% chance the device will fire a deadly bullet and a 50% chance it will do nothing. If the trigger fires, the volunteer dies instantly. According to the many worlds view, the universe splits at the moment of the trigger pull. In one branch, the volunteer dies. But in the other, equally real branch, the gun miraculously jams or the bullet misfires and the volunteer lives. Now, imagine this experiment is set to repeat every second for all eternity. From the perspective of an outside observer, they will quickly see the volunteer die in almost all of the branching realities. But what does the volunteer experience? Their conscious awareness can only follow the path where they are still alive to have an experience. They will witness the gun clicking harmlessly over and over again, each time finding themselves in the branch where they survive against all odds. After 1,000 clicks, 1,000,000 clicks, 1,000,000,000 clicks, the volunteer's subjective experience is one of having repeatedly cheated death. They become a living testament to impossible luck, not because they are special, but because their consciousness is forever anchored to the increasingly rare timeline where their existence continues. This has a startling and indirect implication for how we might experience time. If your consciousness is constantly being funneled into futures where you survive, then from your own subjective point of view, you are on a timeline that seems to bend and twist to preserve you. A near-fatal accident in your past wasn't a brush with death. It was the moment your conscious experience jumped from a branch where you died to the one where you lived. Your personal timeline isn't a single, linear thread, but a path that weaves through the multiverse, always selecting for continuity of consciousness. This could create the illusion of a kind of subjective time travel, where events in your memory feel like they happened to you in a timeline that no longer technically exists for the version of the universe you now inhabit. You remember the car accident, but in this branch, the tree was 6 inches to the left. Your past feels continuous, but it's actually a composite of memories from branches that have since diverged. The theory pushes us to ask a profound question about the nature of reality itself. Is the flow of time we feel actually the trajectory of our consciousness navigating an infinite web of possibilities, always choosing the path forward? It suggests that the arrow of time might be less about the universe's laws and more about the persistence of a point of view. While this is a deeply speculative and philosophical interpretation with no experimental evidence, it reframes time travel from a grand, cosmic endeavor into an intimate, ongoing process that might be happening to each of us all the time without our ever knowing. We may all be time travelers on a personal journey, our lives a story not written in a single universe, but edited together from the countless versions of ourselves that manage to make it to the next moment. But what if the entire cosmos, with all its black holes, quantum loops, and spiraling galaxies, isn't the base level of reality at all? What if our universe is an elaborate construction, a digital reality running on some unfathomably advanced computer in a higher plane of existence? This is the simulation hypothesis, an idea that has leaped from philosophy and science fiction into serious scientific discourse, and it reconfigures the concept of time travel into something that is at once simpler and far more strange. If we are living in a simulation, then time isn't a fundamental fabric of the cosmos. It's a variable within the program, a parameter that the system administrators could adjust, rewind, or fast-forward with the ease of a software engineer debugging a line of code. In this paradigm, time travel would not require bending spacetime with monstrous masses or navigating quantum probabilities. It would be a matter of access privileges. Journeying to the past might be as simple as the system operators loading a backup save of the universe from a previous point in its processing history. They could restore that saved state, effectively resetting the entire simulation to that moment with all its data intact. From our perspective inside the program, it would appear as if time had reversed itself. Alternatively, a more surgical approach could be used. An administrator might grant a specific entity, a simulated person, permission to access a read-only copy of a past state. You could observe the Battle of Hastings or the formation of the solar system as a passive spectator, unable to interact or change anything, like watching a pre-recorded video from within the program itself. Travel to the future could be equally straightforward. The simulators could simply fast-forward the simulation's clock, skipping ahead millions of years of processing in a relative instant to show you the eventual heat death of the universe or the rise of a new civilization. This framework also provides a chillingly elegant solution to every paradox that plagues other time travel theories. The grandfather paradox, for instance, is just a logic error, a glitch that a well-designed simulation would not allow. The system would have rules in place to prevent such inconsistencies from crashing the program. Perhaps any attempt to create a paradox would trigger an automatic correction, the equivalent of a software patch, or result in the offending entity being quarantined or deleted by the system's security protocols. The flow of cause and effect is not a law of physics but a rule of the simulation's architecture, designed to maintain a consistent and coherent narrative for whatever purpose the simulation is being run. This leads to the profound and unsettling ethical implications of this idea. If we are in a simulation, then our entire history, our memories, our loves and losses could be nothing more than data points. The simulators could rewind time to undo a global catastrophe, sparing billions of simulated lives from suffering. But would they? What moral obligation do they have to their creations? Conversely, they might run countless iterations of history with slight variations, observing the outcomes like a scientist running experiments in a petri dish, with our suffering merely a variable in their research. The very notion of free will comes into question. Are our choices truly our own, or are they the predetermined output of the simulation's algorithms? If this is our reality, how might we find evidence of such temporal tinkering? One way could be through uncovering glitches in the matrix, anomalies in physical laws that suggest a simulation struggling to render a consistent reality. Perhaps we might find evidence of a literal save point in the past, a moment where the fundamental constants of the universe appear to have reset, or where the archaeological record shows a bizarre, inexplicable discontinuity that cannot be explained by natural processes. Another clue might be found in the very nature of our reality. The fact that our universe appears quantized with a minimum unit of space and time at the Planck scale could be interpreted not as a feature of fundamental physics, but as evidence of a pixelated digital reality with a finite resolution. The search for a unified theory of everything might ultimately lead us to the source code of the simulation itself, a set of elegant mathematical rules that govern our existence. While the simulation hypothesis remains a highly speculative metaphysical proposition, it forces us to consider that the greatest time machine of all might not be a device we build, but a backdoor we discover, hidden in the source code of reality itself, waiting for the right command to reveal that our past, present, and future are all just variables in a cosmic program. From the mind-bending warping of spacetime described by Einstein to the infinite branching pathways of the quantum multiverse, our journey through these 30 theories reveals a landscape of breathtaking diversity and profound mystery. We've explored cosmic shortcuts forged from the fabric of reality itself, ventured into the chaotic hearts of rotating black holes, and considered the possibility that our entire existence might be a sophisticated simulation. What becomes overwhelmingly clear is that time travel is not a single, unified idea but a sprawling field of scientific inquiry, one that draws from the deepest wells of relativity, quantum mechanics, and cosmology. It's a topic that stretches our imagination to its absolute limit while simultaneously demanding rigorous mathematical proof, while a working time machine remains firmly in the realm of theory and speculation. The pursuit of this idea is far from a frivolous fantasy. It is a serious, ongoing endeavor that forces physicists to confront the most fundamental questions about our universe. What is the true nature of time? Is causality an unbreakable law? How does the quantum world interface with the cosmic scale? Each theory, from the elegant Alcubierre warp drive to the paradoxical bootstrap concept, serves as a crucial stress test for our current models of physics. They are the thought experiments that shine a light on the cracks and inconsistencies in our understanding, pushing the entire field forward in search of a more complete picture of reality. This isn't just about building a machine, it's about unraveling the very operating system of the cosmos. So, where does this leave us, the curious observers dreaming of distant epochs? It leaves us at the edge of a vast and wondrous frontier. The very fact that so many brilliant minds continue to wrestle with these ideas, finding that the math doesn't always say no, is incredibly exciting. It means the door is still open, waiting for that next great leap in understanding, that revolutionary discovery that could shift time, travel from the pages of physics journals into the realm of tangible possibility. Perhaps the key lies in a unified theory of quantum gravity, or maybe it's hidden in a quantum phenomenon we have yet to even discover. The search itself is a testament to humanity's insatiable curiosity and our timeless desire to reach beyond the horizon of the present moment. Now, we want to hear from you. After exploring these 30 incredible ideas, which theory captured your imagination the most? Are you drawn to the cosmic engineering of a stable wormhole, or does the many worlds interpretation offer the most satisfying escape from paradox? Do you think the answer lies in mastering the quantum realm, or is it waiting in the dark energy accelerating our universe's expansion? Share your favorite theory in the comments below and let us know where you think the next breakthrough will come from. The greatest journeys often begin with a single question, and your thoughts are the next step in this ongoing adventure through the